Hello. Hello, my name's Saul Mendoza. I'm a current student at Fresno State attending the computer science program. And today I will be presenting a paper based off of the design of a feasible wireless medium access control communication protocol uh, that would involve, aka via multi-agent reinforcement learning, published from the Institute of Electrical and Electronics Engineers International Conference on Machine Learning for Communication and Networking. That was a lot. The work examines how reinforcement learning can be applied to the wireless medium access control layer, which determines who transmits when and when transmissions occur, and how collisions are avoided when multiple devices share the same wireless channel. Uh, Many recent studies demonstrate strong performance using machine learning for medium access control design, but they often rely on a simulated omniscient environment, uh, meaning that they have complete global knowledge of the network and can freely distribute rewards and observations to all devices. That doesn't exist. Such environment isn't real in wireless systems where devices have limited information and limited communication resources. Um, so the contribution of this work is a learning framework in which the base station computers rewards using only the information it can realistically observe, allowing for a decentralized learning while maintaining strong performance under real world constraints. First, what is a MAC protocol? So how or what is MAC? Um, so MAC stands for Medium Access Control, and it operates at layer 2 of the OSI model. Its job is to decide who gets to transmit when they transmit and how collisions are handled on a shared medium, so within the network. A protocol in general is just a set of rules that devices all have to agree to follow if they want to connect. So MAC protocol is the rulebook that devices use to share the same wireless channel without talking over each other. One important clarification though, a MAC protocol is not just software and it's not just hardware. It is both. The Mac exists as a combination of the NIC hardware and Mac logic implemented in both the hardware and the firmware within the drivers and such. So this is why decisions in the Mac need to be quick, and since they are local and they operate very, very close to the physical layer. Any learning-based Mac has to respect these constraints, otherwise it wouldn't be realistic. So big overview of the MAC protocol and how it is applied. This is one scenario of a MAC protocol, the CSMA/CA with RTS/CTS, aka just Wi-Fi or 802.11 wireless MAC. It's one of the most common wireless MACs protocols. It relies on a mechanism called CSMA/CA, which stands for Carrier Sense Multiple Access with Collision Avoidance. So, summed up, devices listen before transmitting, and they wait for a specific time intervals and use short handshakes to reduce collisions. Uh, the main reason why I'm discussing the CSMA/CA with RTS/CTS because it's common and it represents how wireless devices coordinate and today. It uses fixed rules and controlled handshakes to reduce collisions, but it does not adapt based on experience. This makes it perfect for a baseline understanding of what learning based Mac protocols are trying to replace or improved. So, starting with the transmission sequence, one, the carrier sense. Uh, Listen before you talk, pretty much. What happens is a device listens to the wireless channel. If energy is detected, the channel is considered busy. Um, This exists because wireless is a shared medium. There's a bunch of wireless transmissions going on everywhere. So transmitting blindly would cause immediate collisions. So that's one of the key limitations. A device can only hear what's nearby. Um, and that's if the devices are visible because hidden nodes slash devices do exist. But without getting too deep into that, diffs, DCF end frame, and without getting too into what a DCF means, what happens here is after the channel becomes idle, it's not busy, uh, the device waits for a diffs period. Um, this exists, or its main reason is to prevent devices from transmitting immediately after a transmission ends, and enforces some type of fairness among devices. This delay in the diffs, it's a fixed delay. It's not adaptive. That's when nav and all this comes into play. But without getting too deep into the weeds, step three, request to send. What happens here is the sender transmits a short RTS frame. It includes how long the data transmission will take. The RTS step is pretty small, so collisions here are less costly than colliding large data frames. It is also considered the announcing step, as it announces its intent to transmit. RTS also helps nodes that can hear the sender to prepare to differ, so to get off or to wait or stand by, however you want to word it. Step four, clear to send. What happens here is the receiver replies with CTS if it is ready. During the CTS step, nodes by near the receiver can hear it, and if any other devices are hearing the RTS or CTS, they set a nav timer and they wait and stay silent. And step five, the CIFS, the short inference space. What happens is a very short wait occurs before continuing the exchange. This exists because it gives priority to the ongoing transmission, preventing other devices from interrupting mid-exchange. CIFS is shorter than diffs and has a higher priority because of that. And here in the main goal, the data transmission, what happens here is the sender transmits the actual data frame, and this is pretty much the payload of what wants to be sent or gets sent. Everything before was just coordination, just over some type of overhead on getting the payload or the data or the packet or anything there. If two data frames overlap, the receiver cannot decode either. And then once again, the sifs occurs again. Receiver waits for sifs before responding, and this ensures the ACK or the ACK has a higher priority than the new transmissions. So again, last but not least, the acknowledgement. What happens here? The receiver sends an ACK if the data was received correctly, and the main reason this exists is because wireless is unreliable and ACK just pretty much confirms that everything was there. So if there's no ACK or acknowledgement, it's inferring that there was a failure. So up at to this point, I've explained each component individually. This slide kind of puts the entire 802.11 MAC exchange on a single timeline. Everything starts with the diffs, which is the minimum idle time before any device is even allowed to compete for the channel. If the device decides to transmit, it may use RTS or CTS to announce its intent and reserve the medium, allowing other devices to differ, aka stand by. So after that, CIFS, gives them priority to the ongoing exchange, ensuring that data is interrupted. The data itself is sent in a frame, followed by another CIFS, and finally the acknowledgement confirms successful reception. If the ACK or CTS is missing, the sender infers a collision and backs off before retrying. So the key point is that the entire sequence is driven by fixed timing. So each step has its fixed nav time, uh, predefined reactions, and not by learning or adaptation. It just stays constant. So this timeline shows coordination and how it's achieved today, just through hard encoded rules. So within the 802.11, here's a bigger overview of it being applied to actual devices. 1999, there's a little, I don't know what, and then you could just see it adapt and be able to connect with more and more devices. So when multiple devices share a wireless medium, this is what actually forms a network. Uh, a network exists as soon as two devices can communicate. That's considered a network. Either directly or through intermediate devices. Um, Once devices share a medium, coordination becomes necessary, and that coordination is the MAC's responsibility. So, a little side note, the original 802.11 standard was released in 1977. Since then, various amendments, often denoted by a letter suffix, here we have the example AC and AX, have been introduced to increase speed, range, and efficiency. So, Wi-Fi 5 and Wi-Fi 6. Currently, Wi-Fi 5, which I have, up to 6.9 gigabytes, but realistically, uh, the device ranges from 300 to 800 megabytes per second. And here we can see the 802.11ax, which is currently implemented. It is designed to reliably get near gigabyte speeds to multiple devices. So diving a little bit more deeper into the MAC sublayer, or now we'll touch up a little bit about the MAC address, which is part of the MAC. Um, the MAC address is a unique 12-digit hexadecimal number. Uh, Here we have a little picture example of it. It's a unique identifier, and it's usually one of one within the network. Here we have some key characteristics of the MAC address and the OSI model and where it sits. So what happens when there's two of the same MAC address, or if it's slow and not simple? So what if there's what is done when there's issues, pretty much? So when problems occur within the MAC, here we see I use a mailroom clerk to describe how I handle situations. So like a mailroom clerk, mail is delivered and there's name tags. Does not question duplicates if there's more mail that's getting sent to that person, by all means. It just sends it there. But when there ever is any issues, the operating system would act as the HR. It would assign changes or name tags. The mailroom gets confused if two people have the same tag, what I was just insinuating. HR, aka the OS, would have to fix it. So the OS is not part of any single OSI layer. Like HR in a company, it oversees and supports all layers intervening only when coordination or configuration issues arise. And just like in real life, if HR is involved, something's not right. So diving deeper into what an issue in the MAC protocol would look like, so what the MAC protocol delivers between devices, what a collision looks like. Here is the receiving end of the 802.11 frame structure. It would more than likely find the issue within the checksum, or if not, the lack of the ACK. Uh, Following this slide, what makes a frame a valid frame? A valid frame is one that has a correct structure, arrives without corruption, passes the error check, CRC, FCS, and if any of these fail, the frame is considered invalid and discarded. During a collision, the MAC protocol uses fixed rules instead of learning. And this would then lead to our next slide and what and how machine learning could be applied to this. So now that we've seen how traditional MAC protocols rely on fixed rules, the next question is how learning actually works when multiple devices are involved. In multi-agent learning, each device is treated as an agent that makes decisions independently, but whose actions affect the outcome for everyone else. So as shown here, each agent has a local view of the environment. Uh, they learn by interacting with both the environment and other agents. And depending on how learning is organized, coordination can emerge in different ways. So either through centralized control, which would be this agent here, uh, completely independent learning, or it could be through a hybrid approach. The key idea is that agents do not need explicitly to communicate with each other. Um, Coordination emerges through shared outcomes and feedback. This leads to directly into the question of how multi-agent learning can be implemented in practice, which the paper explores through different learning schemes. So here again, reiterating the points, 802.11 MAC relies on fixed distributed collision avoidance rules, while the proposed machine learning based MAC replaces these rules with learned adaptive policies coordinated through feasible base station centric framework. And here's an image of the interaction and again, the little central part. So again, we moved away from the Mac rules and more focusing on machine learning. The thing that happens is we introduce new problems, aka new overhead. In this context, the overhead means anything added on top of normal data transmission, extra communication, extra computation, or extra information exchange. Many machine learning based Mac designs require agents to share state information, policies, gradients, or global rewards. That's a problem because real wireless networks have limited control channel and bandwidth, and user devices have limited CPU, memory, and energy. If we were to expect a phone or a little AC to or an air purifier to have the same CPU, memory, and energy, or be able to communicate as fast as maybe a local desktop, it would have to adapt and to be able to compete or be worth the overhead. So again, if the overhead is too high, learning-based Macs can reduce throughput, excuse me, and increase latency or only work in simulations. This is exactly why the paper focuses on the feasible machine learning, not just learning that works, but learning that works within real network constraints. So how is it feasible and how multi-agent learning operates specifically at the Mac level or Mac layer? So each device is treated as a learning agent, user equipment, UE. Um, at every step, each device observes only local information, such as the amount of data waiting in its buffer, what actions it took in the past, and the feedback it receives from the base station. Based on this local information, the device chooses an action. It can request access to the channel, transmit data, or remain silent. So pretty much a lot like the Mac already, but it's getting instructions from a central station or a base station. So all devices make their decisions independently, and the network executes these actions at the same time. The outcome may be a successful transmission, an idle time slot, or a collision. So after the outcome is observed, the base station computes a reward. Successful transmissions are rewarded while collisions are penalized. Each device then updates its behavior using this feedback, gradually learning how to coordinate better with the other devices and reduce collisions over time. This is a fundamentally different from traditional wireless protocols where the behavior is fixed. As I've said before, here the coordination is learned through experience rather than enforced by predefined rules. So again, like I said before, no HR is getting involved. This is doing its own thing and it, trying to minimize issues. So this brings the next question is how is this learning process? Should it be organized or what remains practical for and what level would it be practical for real wireless networks to adapt this? So how this learning loop is implemented in the paper. Um, so devices act as a learning agent, as stated before. The shared channels in the environment and rewards are computed at the base station. That this was said in the previous slide. The table shows that centralized training with decentralized training offers the best trade-off between overhead and learning quality, which is why the paper uses it. This table compares different learning schemes in terms of communication and computation and information availability. Fully centralized learning requires too much communication, while independent learning lacks sufficient information. So, centralized training with a decentralized execution provides the best balance, making it the most feasible option for real world networks. And here we have the FCL or the definitions for the table. So why feasibility is a key contribution of this paper. The limitations of prior machine learning based MX and how this paper achieves feasibility. So prior learning based medium access control designs often rely on unrealistic assumptions and high overhead. This paper focuses on feasibility by using existing information, local observations, and no additional signaling. That makes the approach more suitable for real-world deployment, which is the main contribution to this paper. So the authors compare their feasible learned-based medium access control design against non-feasible and baseline approaches using standard performance metrics. The main question is whether feasibility reduces performance, and the answer is no. When the number of devices increases, the simpler feasible method fails to learn effective coordination, resulting in poor packet delivery and long completion times. In contrast, the proposed feasible framework continues to learn stable policies and maintains a strong performance even as more devices are included into the network. So here, more zoomed in onto the previous image, the left column, training convergence, starting with the left plots. These show a cumulative reward during training. The proposed feasible approach, labeled P, converges reliably on both cases. When there are only two users, all learning-based methods converge, although the non-feasible approaches converge slightly faster. However, when we move the more challenge, when we add more, the challenging case here they use three. The difference becomes a little bit more clear. The simple feasible baseline labeled F fails to learn altogether. Uh, they fail to learn altogether, and while they propose feasible method converges similarly to idealized non-feasible solutions. So this shows that feasibility alone is not enough. The reward and design framework matter. So in the middle column, throughput, uh, aka the packets delivered, the shows on how successfully these packets are delivered per episode. For two users, the methods achieve similar throughput, but for three users, the simple feasible baseline performs very poorly, while the proposed feasible approach matches non-feasible methods. This confirms that the proposed design does not sacrifice throughput to achieve deployability. So last but not least, the right column, the time efficiency. The rightmost plots show how many time slots are required to complete the transmission. Lower is better. Again, the proposed feasible method performs on par with the idealized solutions, while baseline feasible method requires far more time slots. This means that the learned coordination is not only correct but efficient. So the key result is that the feasibility does not hurt performance, but poor reward and system does. So summed up, the results show that the feasibility does not significantly hurt performance. The proposed method matches idealized approaches while avoiding unrealistic assumptions like global state sharing. This demonstrates that learning-based MAC protocols can be practical, scalable, and deployable. The main contribution of this paper is proving that learning-based MAC protocols can both be intelligent and realistic. And that is all. Thank you.